All right, this is Notes 9.1, Introduction to Solutions. This is a new unit that we are going over. None of this will be on the test that is on Monday, so do not worry. We just need to get a couple steps ahead because we've got a couple units left and only a couple more weeks left to do it before exams come up. So we're going to get a little ahead and start on Unit 9 before we actually take our test for moles. Keep in mind that the review guide answer key is online on Google Classroom for the test. So if you need help, try to consult that answer key or maybe even YouTube videos to help you with that. I am using apparently some Xbox program that's already built into my computer to record this. So I figured out I can actually record videos. Apparently my gamer tag is Thready Ivy. I have no idea what that means. I don't game at all, and apparently I already have a username for Xbox, and it is Thready Ivy. I have no idea what that means, but yeah, apparently that's me today. So let's go over Notes 9.1. I'm going to choose red as a color here. We're talking about solutions. So we've used quite a lot of solutions in our different experiments. So we've used salt solution or silver nitrate solution, for instance. We've used different solutions in different experiments, and so we're going to delve and we're going to kind of dive into this whole concept a bit more and see what does it actually mean to be a solution. So there's several different terms that we're going to look at, and the first one that we see is solute. So go ahead and follow along in your notes. What I write down, you can write down. Okay, so solute, the definition that we see for that is it's basically what is being broken down. Okay. It's what is being broken down inside of the solution. So let's say, for instance, that you are making coffee in the morning and you put some sugar inside of your coffee. I always take cream sugar with my coffee, so every morning I put sugar in my coffee. And then when I stir that around, that is being broken down into the coffee. And so I refer to the sugar as the solute, and it's being dissolved inside of that coffee. So I'm going to use that word dissolve there. The solute is being dissolved. Okay. Now the solvent is the other part of the solution. It's the watery matrix that I'm putting the sugar into. Okay. And that's technically defined as the most prevalent or the most common, the most prevalent substance. Okay. So there's more water inside of my cup than there is caffeine or sugar or milk. And so the solvent in that case is the water. Okay. And another way that I could put this is it is what is breaking down the solute. Okay. So the solvent is breaking down the solute. Okay. Now, when we talk about a solution, that's kind of those two things combined together, okay? And we refer to that as a homogeneous mixture of two or more substances, okay? A homogeneous mixture of two or more substances. Remember, we've talked about the word homogeneous last semester. That means that it has the same consistency throughout. And so that means that the solute is well mixed into the solvent and it kind of looks the same whether you're looking at the top of the cup or the bottom of the cup. You still have the same ratio of solutes to solvent, okay? So if I were to use a sentence, I would say that a solute dissolves in a solvent and it forms a solution. So that's kind of the equation, if you will, there. All right. Let's draw a diagram of that. Okay, so let's say that I have a beaker right here. That's my beaker. And let's say that I fill it up with water. Okay, you can shade something in right there, or just draw maybe a screw on the top. Okay. We're going to refer to this water as what part? It is the solvent. Okay? If I were to drop salt or sugar or something into this solvent, okay, and it were to start spreading throughout, so you can draw just a bunch of dots, okay, the red stuff is called solute. I'm putting it in there, all right, and the whole thing is referred to as the solution. So that's the entire thing. Okay. Now, a way that I like to remember this, and you can write this if it helps you remembering this, is when I see the word solute, I think that that kind of that rhymes with parachute. Okay, and so I think that it is. I kind of think of it as it's what is parachuting into the solvent. Okay. You can kind of imagine in our little diagram here, if the solutes, if they have like a little parachute there, okay, isn't that cute? They're all parachuting into the solvent, and so they're going into there. So that's how I remember that. The solute is the one that is parachuting in. The solvent, I say, is what the solute went into. Okay, so solvent ends in ent, and so the solute went into the solvent. All right, so the solute parachutes into the solvent, and that's where it went into. That's how I kind of remember those two words. Sometimes it's kind of confusing to remember which one's which, so it's good to have mnemonic there. Now, you're probably looking at these three words, and you're probably just wondering, okay, maybe you're familiar with these words, but it's kind of strange to think in terms of these new vocabulary. But I really want you to take this unit pretty seriously, okay? So I don't want you to take it loosely. You absolutely must make a new unit's resolution about this, okay? So sometimes in a new year, you make a New Year's resolution. Well, I want you to make a new unit's resolution. Maybe you have not been very good with homework, but you need to make a new unit's resolution to solve as many of the problems as possible on the homework. Okay, that's kind of a weird statement. Why did I put that in here? Okay, I didn't actually put that in there to say what I was saying there. What I want to point out is that we use these words kind of all the time. Let's break down this sentence. You absolutely must make a new unit's resolution to solve as many of the problems as possible on the homework. Whoa, that's kind of weird. Everyday words that we use have the same root words that solute, solvent, and solution have in them. Okay, so we see the word solute right here, and it keeps kind of reappearing in different words. It actually comes from the Latin word for to loose, okay? To loose or to set free, and actually write that down, okay? In Latin, it means to loose or set free. So, if I talk about solving a problem, what does that mean? If I'm solving a problem, that means that I'm actually breaking down the problem so that I can understand it better and answer it. If you're trying to solve a problem on a test, you might be scratching out parts, or maybe you're eliminating answers, okay? You're breaking it down. You're thinking about it. You're solving it. Well, a solvent does the same thing. It solves the salt by breaking it down, okay? If we talk about a New Year's resolution, okay, you kind of break down your New Year's resolution into multiple steps, right? So maybe One is to eat more healthy, and two is to, I don't know, do your homework or something, right? And so you break that down and you kind of have a firm hold on what you want to do for the next year. So we actually use the Latin word to break down, to set free in there. Okay, what about the word absolutely? This also uses that word, and this is kind of fun. Okay, so let's say that you were to tell me that you're absolutely going to leave this classroom to go fill up water bottles or something like that. Okay, so let's say that I say, no, don't leave the classroom. You got to stand here, and you're like, nope, I'm absolutely going to go fill up my water bottles. Okay, is anybody going to stop you? No, because you're absolutely going to do that. You're set loose. I mean, you're free to go do what you want because you're absolutely set on doing that, okay? So that's kind of the word that we get there, is when you're absolutely going to do something, you're just let loose and you're set free, you're going to do that, okay? And you can kind of see this in the word solution. You could almost think of it as solution. Okay, it's a solution. A solution of salt water is water that is loosening up the salt molecule. It's breaking something down. You're breaking down sugar, you're breaking down salt. Okay, so that's where we get all of these words. That's why we have a lot of L's and U's and stuff in these words, and that's kind of the background behind these words. And we use them almost every day. Let's look at some examples, and if I went too fast for anyone there, you could pause that. Let's look at some examples of different solutions, and we're going to look at them based off of the phases that they're in, okay? So we can have a solution that is a gas dissolved inside of a gas. Okay, we can have a solution that's a gas dissolved inside of a liquid. We can have a solution that is a liquid dissolved in another liquid. We can also have a solution if you put a solid inside of a liquid, kind of what we've already been talking about. You can even put a gas in a solid if you would like to. That is a solution as well. And you can also do a solid inside of a solid. That is another type of solution. Okay. So what are some examples of this? Let's look at this. What's an example you think of a gas inside of a gas? Well, air. You're breathing it right now, right? Okay. The solvent is the most prevalent gas. And so what is the most prevalent gas inside of the air? Well, it's nitrogen. Nitrogen's the most prevalent gas, and the one that comes after that is oxygen. So you could list several different gases here, but you could say that oxygen is dissolved inside of the solvent of nitrogen, right? Okay, let's think about a gas inside of a liquid. Typically, liquids that we're looking at is water. Water's involved in a lot of these. Okay. And one typical one that you're probably familiar with, well, that you are familiar with, is if you put carbon dioxide inside of water, you get bubbly water, okay? This is the whole solution behind soda pop, or soda, or soft drink, or whatever you want to call it, depending on where you're from. This is, yeah, behind Mineralwasser here in Germany. And so if you're drinking bubbly water, mit Gas, okay, that has the gas dissolved inside of the liquid. And so, yeah, this is like just the most delicious solution. There is just probably nothing as satisfying as just drinking like cold soda out of a glass bottle, especially after like a hike or something. Like, just pause and think about that. That's chemistry. That's delicious. Okay, let's move on to another one. I used this solution down here over the weekend for Easter. I made a bunch of deviled eggs. And what that involves is taking a bunch of yolk and mixing it with mayonnaise and mustard and vinegar. Okay, I used vinegar inside of that mix too. Vinegar is a solution. The solvent is water, And it basically is when you combine acetic acid into water. And so the water is kind of spreading that out, setting loose that acetic acid. The acetic acid is freely flowing inside of that water. And that's what vinegar is. Okay. Ocean water is another example, and this is of a solid inside of a liquid. Okay, we know that the liquid again is water. That's why we call water the universal solvent. We see it all the time. What is a solid? That would be in the water. Well, sodium chloride or salt, right? So it is salt water, so we see that dissolved inside of the water. This is kind of a weird example, gas inside of a solid. There's actually a solution that you can make where you put hydrogen gas inside of platinum. I believe that it's used for cancer research, if I remember properly. But platinum is the most prevalent material, so we would refer to that as a solvent, whereas H2 was a solute. Okay. The last one that we will go over here is one that we did at the beginning of the semester, the first semester, and that's when we did our experiment on brass pennies. Okay, remember that brass is what we call an alloy. Okay, an alloy is a physical mixture of different metals, right? What was the most common metal that we were looking at when we did that experiment? It was copper. Okay, the penny was made up of copper, and so that was the most prevalent one. It was on the outside, but we physically mixed in some metal. Anyone remember what the metal is? It was zinc. Okay, so the zinc was dissolved into the copper when we physically mixed that through heating. Okay, so that in and of itself was a solution when we made those gold pennies. That's what it turned out to be. Now, this shows us, just looking at this example of brass pennies, was the brass penny experiment, was that an example of a chemical or a physical change? It was a physical. Okay, so go ahead and write this down because this is important. Dissolving is a physical change. It's not a chemical one. Okay. If it were chemical, you would be creating new substances with new formulas, but this is actually just a physical change that is happening inside of this example with the alloys and with all solutions. All right, so that's the table on examples and looking at the phases right there. Go ahead and flip your page over and let's start working on the back. Again, you can pause this anytime that I'm going too fast. All right. So, I'm drinking some mineral water right now, carbonated water. So I'm drinking a solution. All right, so like dissolves like. You've probably heard this if you've been in any science class before. It's kind of a typical thing that people like to talk about, and we're going to examine the chemistry behind this. You probably know if I had a beaker and it were full of water, color it like water, okay? And if I were to pour oil into that beaker, what would happen? The oil is not going to dissolve into the water. The oil is actually going to remain on top. And one of the reasons for that is that water is a polar substance and oil is a nonpolar substance. Okay, so the nonpolar will not dissolve into the polar substance, and this is a theme that we see throughout nature. Okay, so this has its exceptions, of course, but for the most part, usually what we see is that non-polar substances like to form solutions with other non-polar substances. And we'll review a little bit what polar means, right? Okay. We also see that polar substances like to form solutions with polar substances. So oil is non-polar, water is polar, so the oil does not like to mix in with the polar water. Now, thinking about the word polar, again, just to remind us, thinking about other words in the English language that we use. Okay, if I have the Earth right here, and here we go, there's Florida, South America. Let's see how accurate this is. Here's Africa. Here's the boot of Italy. That's kind of a boot. There's England, red dot. Alright, so there's the Earth. Right here, or about right there, okay, we're going to refer to those as the poles, right? And we refer to that as the North Pole, the South Pole, because they're extreme opposites. They're extreme ends on the planet, okay? And we refer to the word pole in the same way to molecules, if they have extreme ends to them. And those extreme ends are caused by the electrons. So let's review that just a little bit. Molecules can have three main types of bonds in them. Okay, we're going to see non-polar, covalent. Okay, what's the second one? It's going to be polar covalent. And the last one is ionic. Okay, so we have nonpolar, covalent, polar covalent, and ionic. And as we move across this table, we kind of see an increase in those poles, in those extreme differences in that polarity. We see that increase across the table in a sense, right? Well, let's go through an example of a nonpolar covalent molecule. Can you think of one? Let's think of hydrogen gas. All right, that's just H2. When we talk about nonpolar, what that means is that there's an equal distribution of electrons. And when we talk about covalent, that means that there's a sharing of those electrons. So this is an equal sharing of electrons inside of the H2 molecule. Okay, this means, you can write this in this box right here, that it has no charge. So if I want to draw a Lewis structure of that hydrogen gas molecule, this is what it would look like. And we have these two electrons in the center, okay? What they're doing is they're kind of swirling around those two hydrogen atoms and in between them, and they're just kind of equally being shared, right? They're just going around in an equal manner. Why is that? That's because the electronegativity, so remember, that is the love of electrons, okay? The electronegativity of the hydrogen here is the same as this one over here. So they both love electrons to the same degree. So they're both going to share those electrons equally. All right. So this is nonpolar. And this actually affects how this gas will dissolve, because it's more likely to dissolve in a nonpolar solvent. Okay. Let's look at a polar covalent one. What's like the prime example of a polar covalent molecule? It's going to be H2O, right? Water. We keep coming back to this molecule. And what we see in this is there's actually a difference in the oxygen and the hydrogen with regards to their love for electrons, okay? There's actually a difference there. And so because of that, we see that there's an unequal sharing of electrons. And this ultimately affects how it acts as a solvent. Okay, so because of this unequal sharing of electrons, that means that it has slight charges. There's slight charges inside of this molecule. Now, we've drawn this before, and so let's just draw this again. I'm going to use red here for oxygen because that's usually the color that people use. So here I have an oxygen atom. I'm going to label him O right there. And he's bonded to 2 H atoms. Okay? Now, which one has the greater electronegativity? The oxygen. So O loves electrons more. Okay? He has greater electronegativity. So what's going to happen is that those electrons are going to spend more time swirling around the oxygen than they are around the hydrogen, because the oxygen loves to spend time with those electrons just a little bit more than the hydrogens do. Okay? And we used some symbols to talk about the charge that results, right? If more electrons are around the oxygen, then we know that it has a slight negative charge. And we use the lowercase delta to symbolize that. So a lowercase delta, slight negative charge. Whereas on the hydrogens, we have a slight positive charge and a slight positive charge. Now, we know from hydrogen bonding that this affects how the molecule interacts with other molecules that contain hydrogen, and it also affects how it interacts with other molecules just in general, if they're polar or not. Now, let's look at an actual animation of what this particular substance looks like, okay? This is a diagram of a water molecule, okay? And what you can see here is that the red dots on the outer ends, what are those? That's the hydrogen atoms, okay? So you have these hydrogen atoms on the outside of this molecule, the one in the foreground there. They're essentially just protons with electrons, right? They don't have any neutrons in them. That's why they have an atomic number of 1. What's that in the middle? That's the oxygen. The oxygen is in the middle of this atom with its protons and neutrons. 16 of them, right? And the yellow dots are representing the electrons, okay? Where are the electrons mostly inside of this model? Well, they're in the center more, right? They're kind of surrounding the oxygen more than they are the hydrogens. And that's because all of these protons in the center right here, all of those protons are going to be attracting those electrons more than the protons on the hydrogens. So you see a polar molecule resulting where the electrons are more extremely in the center of the molecule than they are on the outside. And so you kind of get these positive poles on the outside and these negative poles on the inside of the water molecule. All right, now let's move on to ionic. Ionic, prime example, always sodium chloride, okay, NaCl. And what's the word that we use to describe an ionic bond? Not sharing, stealing. It's stealing electrons. Okay? And that means that this compound does not just have slight charges, okay? It involves complete ionic charges inside of this structure. And so what we've seen is that we have a sodium and we're going to box him in this Lewis structure diagram because he has a positive charge. And he completely lost his electron to chlorine. And so chlorine's over here, and chlorine normally has 7 electrons, but because he stole 1 electron from sodium, now chlorine looks like that, and so he has a negative charge. So those complete charges right there are going to affect how this sodium chloride interacts with other molecules, like water. Okay? So, let's revisit our rule. Usually, polar substances like to form solutions with polar substances. H2O is a polar substance. We can kind of consider sodium chloride to be a polar substance, right? Because we have a positive end and a negative end. It has a polar nature to it, right? And so that means that these are likely going to form a solution, which makes sense, right? Like a solution of salt water. If you put salt into water, it's going to dissolve. Why? Let's look at this a little more closely. Okay? Here's the steps to how it's gonna work, all right? So the first step, let's say that you drop salt into water. What's gonna happen next? Well, we know that the water molecules are very polar. Because they are polar, they are attracted to other polar molecules. Water molecules are very polar and attracted to other water molecules, okay? So we see this negative slight charge on the oxygen. Guess what that's going to be attracted to? That's going to be attracted to this positive charge on the sodium, okay? So, water molecules are very polar and attracted to other polar molecules. So when this salt, which is pretty polar, right, it gets dropped into the solution, what happens is that the water, whoops, there's a keyboard. That did not mean to happen. Okay, the water pulls on the sodium and chlorine ions in that compound. And when it pulls on them, because it's attracted to them, it actually weakens the ionic bond in NaCl. Okay, so water's kind of doing a tug of war with the Na and the Cl, and it's weakening that bond. And so what's going to end up happening is the sodium and the chlorine, let's do our little symbols there, sodium and the chlorine are pulled apart. Okay, sodium and chlorine are pulled apart, and the water molecules start to enter the crystal and dissolve it. All right, they're dissolving it. When you solve a problem, you pull it apart to figure out what the answer is. When water dissolves the salt, it pulls it apart. Okay? This can be represented in a pretty simple equation, in a sense. One way that we could write it is if we have NaCl here, and in the center we put H2O over the arrow. We just kind of assume H2O is there. H2O is causing this action to happen. And it's actually breaking this compound down into its respective ions. And so what happens here is you have Na plus, and put a space there for a moment, plus Cl negative. Now, we learned about some terms that we use, some symbols that we use with things like this, and we're actually going to label this AQ. AQ. What does AQ stand for? It stands for aqueous. Okay, aqueous, just like water, aqua. Okay, that means that it's dissolved in water. NaNCl is dissolved in water. So the Na and the Cl were together before by that charge being attracted, and now there's just water stuck in between those. Let's draw a picture of what that actually looks like. Okay, I'm going to use green to represent Na. So let's draw a salt cube. Okay, you know that you have the cations and the anions being alternated inside of an ionic crystal. So it kind of looks like this. Let's make the chlorines negative here, and let's make the sodiums positive. Make sure that they're alternating like that, right? And then we've got the H2O, and you've now submerged your solute into your solvent. So your solute's the salt, solvent's the water. You've submerged it into that. What's going to start happening? Well, let's look a little closer. Let's draw it like this. I'm going to draw my sodium ion as a circle here. This represents my sodium ion. And I'm going to have my water molecule approach this and start to pull on it. It's setting it loose. It's dissolving it. Okay? What's going to happen? I'm going to draw my oxygen right here. And my hydrogen's right here. Draw a little Mickey Mouse water molecule, okay? Now we know that at this end we have a slight negative charge. So the water molecule arranges itself in that manner. Go ahead and draw another one down here. Upside down Mickey Mouse. H's, and let's do a delta negative right there. So you can kind of see this attraction happening right here because we got this plus and this minus, and so the water's playing a tug of war. Let's draw one last one. Definitely draw this one. We've got an oxygen right here. Sideways Mickey Mouse. Hydrogen right here. And let's do a delta negative. Let's draw the delta positives on this one. Delta positive on the hydrogen. Delta positive. There's a slight charge on the hydrogen because the electrons are being pulled away by the oxygen. Now, what do you think's on this other side of this water molecule? We have a Cl negative atom, right? We have a Cl negative ion. That negative charge is going to be slightly attracted to this positive charge right here. So this water molecule is wedging itself into the crevices of this crystal and pulling apart those ions. So it's dissolving, the salt. So the way that we're actually going to draw this water molecule is we have our O, and this time the hydrogens are actually facing towards the chlorine. Delta positive. Delta positive. Here the oxygen's kind of facing away, and we have our hydrogens most closely related, or most closely associated with that chlorine there. Okay, so now that is how the water wedges itself into that molecule. And that's what happens when you drop salt into water and it breaks down. Eventually you can't see the salt anymore because it separates into its sodium and its chlorine ions. Now, let's look at a different model of this, okay? Here's another model. Here you can see this blue atom, this blue ion. The white hydrogens are surrounding that one. Okay, notice you have the white right here is pretty close. So the hydrogens, remember, are positive. So what must the blue atom be? That's got to be chlorine. This green atom right here has the negative, slightly negative poles of the oxygen here attracted to it. So that means that this must be sodium positive ion. All right, is that what it is? Well, let's actually, hold on, let's look. Nope, that's not what I want. Stop it. All right, let's zoom him around here. All right, look, that's exactly what it was. The chlorine negative is the blue, so you see those negative ions, and the positive is the green. So at first it looks like this, right? Where you have the positive and the negative in this ionic crystal. That's what a salt crystal looks like. They're in this lattice, remember? And then what starts to happen is these water molecules start to wedge themselves in between those atoms. And so the hydrogens are attracted to the chlorine, the oxygens are slightly attracted to the sodium, and once they get in there, they start to let loose. They're freeing it. They're solving it. They're dissolving it, all right, inside of that solution. And so the water is the most prevalent, and it's invading that crystal and breaking it apart. So this is the whole reasoning behind the rule that polar substances like to form solutions with polar substances, because if you can have something that has slight positive and slight negative charges, those slight positive and negative charges are going to play tug of war with the slight positive and negative charges of the substances that you're dissolving, or the solutes, right? So the solvent's playing tug of war with the solute. So here's a question. What about this molecule right here? All right, this is sugar. You know from experience what sugar does when you put it in water. Do you expect sugar to be a polar molecule? Well, yes, it is, all right? This sugar molecule is polar because you have so many oxygens and hydrogens in here. And those oxygens are just playing tug of war with those hydrogens, and they're just kind of like, hey, we really want those electrons more than you do, and hydrogen's like, fine, you can take them, and so they're kind of being unequally shared there. Well, when you have that unequal sharing, you have that polar charge happening, and then this water molecule comes in, and he is also polar, and so he has that slight charge, and so what he's going to do is he's going to rearrange himself so that his positive hydrogens are kind of close to that negative oxygen, and he's going to pull him apart. Now, he actually doesn't pull the entire molecule. He doesn't rip the molecule to shreds, but he actually rips the molecules from each other. So a glucose molecule is made up of multiple sugar molecules. Sorry, a glucose crystal is made up of multiple sugar molecules, and so it's actually separating those molecules, not the atoms necessarily. But because it is polar, that allows the water to grab onto it and to pull it. And so polar substances, they play tug of war with each other, so that's why they dissolve. Non-polar substances, they'll just form solutions with other non-polar substances. So that's the whole reasoning behind like dissolves like. Okay, you have completed your notes of this. So we've, as just a review, we've gone over the three terms, what a solute, solvent, and solution are. We've looked at 6 different examples of what those are, and you can find any phase inside of another phase, and those elements can still be considered solutions. When we looked at alloys, that process was a physical change and not a chemical change. Even when we're dissolving things like sugar and you're pulling the molecules apart from each other, that's just a physical change that's happening. We have the rule that like dissolves like, because the electrical charges determine a lot of that. And we reviewed a little bit about dipoles and poles and how those affected this whole rule. And now you know why when you put a sugar cube inside of your coffee in the morning, if you do that, you know why that gets pulled apart inside of that mug. All right, I will see you guys next week. Enjoy your weekend.